Good morning, students. Welcome back to our physics classes. During the last two classes, we were discussing about second law of thermodynamics. We have seen the two different statements for second law of thermodynamics, and based on the first statement, the Kelvin-Planck statement, we have defined a heat engine, and we have seen Carnot's heat engine and the structure and working of Carnot's heat engine. And in the last class we defined the efficiency of Carnot's engine, work done, net work done, and the efficiency of Carnot's engine. And we have stopped with the concept of Carnot's theorem. So Carnot's theorem says if many heat engines are designing between two similar sink and source, the reversible Carnot's engine will have the maximum efficiency, which means no other heat engines can have efficiency more than a Carnot reversible engine working between the same source and sink. You know what is a source, what is a sink, and what is the function of a source and sink in a heat engine. All these matters you are knowing. And we are interested in the different statements of our second law of thermodynamics. First law, the Kelvin-Planck statement, it is impossible to convert the whole heat energy supplied to a system into useful work. That is provided by Kelvin and Planck, and this is known as the Kelvin-Planck statement. And based on this statement, we designed our heat engine. And during the working of heat engine, it is clear that 100% efficient heat engine is not there, which means it is not possible to convert the whole heat energy supplied to a system into useful work, which is very in agreement with very much in agreement with the second law of first statement of the second law of thermodynamics, that is the Kelvin-Planck statement of the second law of thermodynamics. Okay, and Cauchy's statement said that it is impossible to transfer heat energy from a cold body to hot body without the help of an external source. So here we have to be more focused on this statement. It is impossible to transfer heat energy from a cold body to hot body without the help of an external agency. What it says? It says that to take heat from a hot body to cold body, no external agency is required. That means help from any external agency is not required to keep or to take heat from a hot body to cold body. Hot body is a high temperature system and cold body is a low temperature system. So we can say that heat can easily flow from a high temperature system to low temperature system. Heat can easily flow from a high temperature region to low temperature region. It is a spontaneous process. It is not required any external initiation. But when you talk about the reverse process is impossible according to Cauchy's statement if it is not guided by or aided by an external source. If an external work done is there, then it may possible taking heat from cold body to hot body. Otherwise, it is not possible. Spontaneously, heat will not flow from cold body to hot body. It is not a spontaneous process. So, based on this statement, that means the Cauchy's statement, it says to take heat from a cold body to hot body, we need an external source. So, based on this principle, scientists design a device, and that device takes heat from a cold body to hot body. It takes heat from a cold body to hot body with the help of an external work done. with the help of an external work done. So, but yes, you can call that system as, or you can call that device as refrigerator. That system as refrigerator. So, refrigerator is a system or a device which can take heat from a cold body to hot body, taking an external aid. That means taking the help from an external work done. So, suppose schematically we can represent the working of a refrigerator. So, you are having a source. You are having a sink also. And here you can have the refrigerator. Okay. So, from sink, refrigerator takes, see, Q2 amount of heat. Refrigerator takes Q2 amount of heat from sink, which is kept at a lower temperature T2. Okay. Now, a work done on refrigerator. A work is done on the refrigerator as W. A work is done on the refrigerator as W. Then, it can inject heat into source as Q1. It can inject heat into source as Q1. Which means refrigerator takes Q2 amount of heat from sink, the cold body, and ejects Q1 amount of heat into the hot body, the source, with the help of an external work done W. With the help of an external work done W. So, from the schematic diagram, you can write it as Q2 plus W, Q2 plus W equal to Q1. Q2 plus W equal to Q1, and W is equal to Q1 minus Q2. Q2 is equal to, Q2 plus W equal to Q1, and W is equal to Q1 minus Q2. We have W is equal to Q1 minus Q2. And when you are taking Q2 common, Q2 into Q1 by Q2 minus 1. Q1 by Q2 minus 1. And you know Q1 by Q2 is equal to T1 by T2. So, W is equal to Q2 into T1 by T2 minus 1. Q2 into T1 by T2 minus 1. So, this is the work required to take Q2 amount of heat from the sink by a refrigerator. So, W is equal to Q2 into T1 minus T2 T1 divided by T2 minus 1. Q2 into T1 divided by T2 minus 1 is the work required by an external agency to take Q2 amount of heat from the sink. Q2 amount of heat from the sink. So, this is the requirement of a refrigerator. Means the components are same. We are having a source, sink and refrigerator, and the purpose is only the difference. And similar way we can express the heat engine also, right? Schematically, you can express heat engine also. Here you have source, heat engine is there, and our sink is here. Source is kept at a high temperature T1. Here also source is kept at a high temperature T1, and the sink is kept at a lower temperature T2. From source, heat engine takes Q1 amount of heat Q2 amount of heat is rejecting into the sink. W amount of heat is giving out from the heat engine. Here refrigerator intakes work done and the heat engine gives out work done. Here also the equation is same, that is Q1 equal to W plus Q2. Q1 is equal to W plus Q2. In both the cases the equation is same, but the direction of work done is different and the direction of heat flow is also different. In heat engine, heat is flowing from hot body to cold body, giving out a work done. And in refrigerator, heat is flowing from a cold body to hot body by taking an external work done. Okay, so that is the difference between heat engine and refrigerator. Heat engine and refrigerator. In case of heat engine, we have defined its efficiency. What is efficiency? Efficiency is output divided by input. You are giving to heat engine heat energy as input and you are getting an output from that heat engine in the form of useful work. So here you can't say that you are giving an input into the input you are providing, that is a work done. But you can't say that the input is Q2 amount of heat and you are not getting an output as in the case of a work done or useful work done. But here the purpose of a refrigerator is it has to take as much as heat from cold body and with a expenditure of a very small amount of work done. Which means suppose you designed a refrigerator which is taking only very less amount of heat from a cold body and for that you have to give a large amount of work done externally, then you can't say that it should be that device is not a good refrigerator. And a good refrigerator takes as much as possible heat from a cold body with the expenditure of a very small amount of work done. That means the performance of a refrigerator can be defined in this way or can be measured in this way. So instead of efficiency, here you can define coefficient of performance. You can define coefficient of performance. Coefficient of performance for a refrigerator. So that is coefficient of performance K is equal to Q2 divided by W. It is mathematically expressed as Q2 divided by W. What is Q2? Amount of heat taken from the cold body. What is W? The work required for that. So the amount of heat taken from a cold body by a refrigerator per unit work done on the refrigerator. That is coefficient of performance. That is defined as the coefficient of performance. And from the equation itself, it is clear that whenever Q2 is as large as possible, then Q should be possible with a condition W is as minimum as possible. Which means to make a good performing refrigerator, what to do is you have to design in such a way it can take maximum heat from cold body with the expenditure of very small amount of work done. In such a case, you can say that refrigerator is a good refrigerator. Okay, and have you ever seen this refrigerator? What a silly question. And all of you are having this refrigerator at our home, but we are not using the term refrigerator to mention that device. Usually we are saying that the fridge, the name as fridge. The fridge is very similar to, or it is only the refrigerator. That means fridge is a refrigerator. Remember, fridge is the company, first company who made this refrigerator commercially. Means for this commercial purpose, selling purpose, fridge is the first company to manufacture refrigerator. So automatically that name, brand name came as the device name. But remember, the device is not fridge and the device is refrigerator. Device is the refrigerator. Okay, so that is the refrigerator which can convert, which can take heat from a cold body to hot body by taking an input from any external agency as in the form of a work done. So coefficient of a good refrigerator, the coefficient of performance of a refrigerator is defined as Q2 divided by W. Q2 divided by W. You can take it as Q2 divided by Q1 minus Q2. Q2 divided by Q1 minus Q2. And Q2 you can express in terms of temperature as T2 divided by T1 minus T2 divided by T1 minus T2. So this is refrigerator. So this is a simple chapter, and in this chapter we have seen what is second law of thermodynamics. A special chapter is allotted in your textbook for the second law of thermodynamics, and there you find two different statements of second law of thermodynamics. Based on these two statements, we have defined two devices, heat engine and refrigerator. Heat engine working and everything we discussed in detail, and the refrigerator is very similar to the heat engine, but some conceptual difference is there, that is the direction of heat flow and the direction of work done. So in refrigerator, heat is flowing from cold body to hot body by intaking work done. In case of a heat engine, heat is flowing from hot body to cold body. Same time, work done is giving as an output. So heat engine is a device which can convert heat into useful work. But our refrigerator is a device which can convert or which can take heat from a cold body to hot body. Okay. So that's all about thermodynamics. So in thermodynamics, we have seen what is a thermodynamical system, how you can define a thermodynamical system, what are the state variables, different types of, what is a thermodynamical process, and different types of thermodynamical processes we have defined. From there, you designed two thermodynamical processes as isothermal process and adiabatic process, and we have seen the properties of isothermal process and adiabatic process separately in detail, and what is the how you can express a isothermal process and adiabatic process, isothermal curve and adiabatic curve, then work done in isothermal process and adiabatic process, then cyclic process and reversible process more we have defined, and based on that we have defined the second law of thermodynamics. Then specific heat capacity, before second law of thermodynamics, specific heat capacities Cp and Cv, then Mayer's relation, then second law of thermodynamics, reversible process and cyclic process. These two processes are used there to find out the to explain the working of heat engine and refrigerator. See, all these are there in the thermodynamics chapter, means concept, thermodynamics. It is given in 3 different chapters, but all coming under thermodynamics. Now, we have seen that whenever we are defining a thermodynamical system, we have said that it is a gaseous system. So, what are the properties of gaseous system? That is explained in the next chapter, and that we will start in the next class. So, we are winding it now, and we will meet the next class. Before that, you go through the concepts in thermodynamics and make thorough the ideas of thermodynamics. Okay, bye.